it's obvious, so there are some obvious thoughts on the slide. Numbers are fundamental to mathematics and science. So they can represent probabilities, which are numbers from 0 to 1. We can represent physical measurements. They can represent mathematical quantities. Like, well, we cannot represent exactly square root of 2 in the computer, so you need to have some approximation. So real numbers, if you remember, probably first year of mathematical analysis, we typically describe some definition and properties of real numbers as infinite fractions. But in computer, you only have infinite memory, so you need to have some finite representations. So 2000 years ago, Babylonians, they used positional number systems with the base 60, and we still have 60 seconds, 60 minutes from that. Maya, they had, as the base number, they had 20. Romans, they actually didn't have positional number systems. So the Roman labs actually quite bad for computation. You want to do some computations with them with Roman numbers, you can only number them. 1, 2, and so on. So it's not so-called positional number systems. So the computers work with positional number systems, and they represent everything with bits. So everything, including real numbers, has to be converted to zeros and ones. So there have been systems where the base for the integers was not 2 but 3. I think there was 1 or 2 computer systems that used ternary computations, but it was abandoned. Everything is binary. And well, besides classical bit representations, there are other computational devices right now. Maybe somebody knows. It doesn't work with bit representation, but with something else. Who knows? That represent quantities with something else. With what you can represent numbers for computations.
What is a qubit? It's like not the speed wave.
Yeah, but what is physically?
It's a state of something.
Yeah, it's a state of something, but basically what you want to do, you want to utilize a physical system, in this case a quantum system, to perform some computations for you. So when we are talking about classical computers, we store everything in bits, in whatever way, like transistors, and so on. Or but you can use also try to use quantum systems to represent the quantities that are working with. And except quantum, what else you can use for computations in principle? So any physical system has some information about itself, right? So you can use these, so I will not go into the details, but basically, in fact, what we have in our computers that you're all working with, and all of the central processing units and RAMs or whatever, they utilize with a very specific architecture, but it's not because this is the only way. It's because we know how to build this, we know how to write software for them, and so on. But you can, and this is a very popular trend right now in trying to use different means of physical systems for computation. It can be quantum systems, it can be actually some optical devices. You can put a camera, then you can put something between the camera, between the projector and the screen, then you can take a photo, and it actually implements a certain computation. So instead of modeling a certain physical system on a computer, you can use a physical system to model some computation, some computations. So you can use optical, you can use analog circuits, so-called neuromorphic computations. And for all of them, you have to develop absolutely different algorithms. You have to develop absolutely different algorithms for quantum computations, you have to develop absolutely different algorithms for optical computing, and you can Google actually what is optical computing, quantum computing, many algorithms, including actually many algebra algorithms. But this is a completely different thing. So what we are talking about most common nowadays, CPU, maybe GPU, but there is also the wall see what you can do with modern computers. They're again getting huge, they again consume a lot of energy, they cost a lot, and it's quite natural that scaling beyond this limit may be not even possible. So if you want to do more computations, you want to do it faster, you want to train super large models, but you don't want to spend hundreds of billions of dollars, then you can invest these hundreds of millions of dollars into alternative computational resources, including optical and quantum and neuromorphic computing. And these, for some of these, they're actually real devices. So there are actually access to real quantum or quantum-like computing devices. We should program with Python, and it will, I don't know, solve some linear system. It looks like a miracle. So from the viewpoint of a programmer, you just run a Python code, and then some superconducting machine does something, and you read the result. But it actually exists. Or you could work with optical computing as well. So that's a separate topic. If you're interested, we have some projects in this direction, so you can ask me if you need more details. So what I'm trying to say, that even if something is well known for many, many years, that we have bits and we work with bits, at some point, the whole paradigm can change completely. And now, maybe in several years, we will not sit with these MacBooks or whatever. Maybe 10 years, but with some quantum, whatever, light in it. Maybe, I don't know. So let's get back to the ground.